They're terms which often get confused. And so I'm really focusing on multiple models, but I will touch on multimodal ones. So first of all, I'll ask you to bear with me a little bit. I actually managed to break one of my teeth this week. And so I'm a little bit snuffy. So apologies if the audio isn't so clear. So first of all, I'll just start telling you a little bit about myself so you've got some idea of who's talking to you so you know how much credence to give to what's being said. So I've spent most of my career either designing ASICs or designing FPGAs. And for those of you that do that, you know there's a lot of crossover between the two. I then moved into leading teams designing products, primarily with large ASIC or FPGA content. And that's when I then started picking up embedded and DSP skills. And then for the last 4 or 5 years, I've been doing a lot of work in AI. That started just before COVID, doing AI primarily on military applications. And then I was involved in a project during COVID to do an AI recognition system to very quickly detect the COVID virus. Since then, I've now been with Arrow for just over 2 years. Arrow is the world's largest electronics distributor. And you may think, why does someone that designed chips work for a distributor? A part of Arrow a lot of people don't realize is we have about 3,500 design engineers providing a range of design services to help our customers get their products completed on time. For those of you that would like to connect, this QR code will give you all my contact details and allow you to also connect with me on LinkedIn. Very happy to take questions as I talk, or if you would rather save them for later, you can either email me or give me a call. Or if you'd like to come and talk today in person, I will be at the show for both days, and my booth is J1. Okay, so what are we going to talk about today? I'm going to very briefly talk about what an AI model is. Then I'm going to talk us through why we use multiple models, some of the hardware efficiencies that you can get from using multiple models. And then, like I said, I'll touch briefly on multimodal, and just because that term's often confused with multimodal, and I just want to make sure you're walking out with a clear understanding of what those are. So it's almost embarrassing every time I put this up because I'm sure everybody has seen it 100 times. However, every time I give a talk, somebody hasn't. And so it's always worth just quickly refreshing our minds, especially, as embedded engineers, when we talk about AI, invariably we already know we're probably talking about deep learning, potentially machine learning with some stochastic method, but normally deep learning. However, what we have to realize is that when we speak to people who aren't embedded engineers, they also need to know what we're talking about. And to them, AI doesn't necessarily mean deep learning. So very quick run through. Artificial intelligence is anything that mimics human behavior. So if you take a really simple piece of human behavior, like opening a door when somebody knocks on it, if you rigged the door up with like some sand and it like a tilt table so that whenever you knocked, the sand started falling and the door opened, something like out of Indiana Jones, that's artificial intelligence. The door's behaving the way a human would. It's opening when it's not. Doesn't even have to be a computer. Then we have a wide range of very simple computer programs that behave the way we would behave for very simple instances. And so they're also artificial intelligence. Machine learning, that's when instead of us programming directly how the behavior should be, we use some form of learning process to instigate that behavior inside the algorithm. And then finally, deep learning, the statistics and mathematical algorithms used become neural networks, which is just a particular type of way of organizing. If you're interested in knowing about this in a little bit more detail, I had the pleasure of doing a talk here last year. That talk's still available, and that goes into some of these details. And I wouldn't say it's required vision or required viewing before seeing this, but it will give you a little bit more detail than what I'm sharing now if you're interested more in the basics of AI models for embedded engineers. Now, even a year ago, I probably wouldn't have added this box. I mean, we're at Hardware Pioneers, we're all embedded engineers. Why on earth would we talk about generative AI? You can't do that at the edge. Well, you couldn't several years ago. Now you can. And that's happening for kind of two reasons. One, the scientists and the researchers in the field of AI are taking very complex frameworks and they're making them simpler and easier to run on lower specified hardware. At the same time, the clever ASIC engineers are creating hardware that's got more performance. And what we're seeing happening is that the models are becoming less complex and the hardware is becoming more capable. And between the two, we have a crossover. And there are now multiple different suppliers that provide chipsets that will allow you to run generative AI at the edge, which is why it's now appearing in our talks. So let's imagine we're design engineers. Hopefully, that should be easy for most of you in the room. Um, there are lots of problems that we can solve, and we can solve them really well. However, there are other problems which are difficult for us to imagine how to solve. Even some of the really simple ones, like human handwriting recognition. To solve that using classical methods without neural learning, you need to be looking at things like discrete cosine transforms. You need to be doing color correction, contrast matching. You need to be looking for curves, looking for edges, understanding what those curves and edges mean. As a design engineer, you could do that, but it's very time consuming. And it's much better instead to take vast amount of data and put it into very large compute resources and have it work it out itself. If you remember at school, maybe designing fast Fourier transforms, or even something really simple like a bandpass filter. If you're designing a bandpass filter, you've got some RC networks, and you've maybe got like 6 or 8 coefficients to play with. And you can use MATLAB. Other tools are available, but use something like MATLAB to draw your RC circuits, have your 8 coefficients. You move your coefficients up and down. You can get a little slider to do it, and you see the shape of your bandpass filter move, or what frequencies it'll pass, which ones it won't, how sharp it'll be. An AI model is exactly the same, but instead of there being 8 coefficients, even the small ones have hundreds of thousands of coefficients. And the reason that we can run generative AI at the edge today is because there's now a Gen AI model that has 7 billion coefficients, and that's small for generative AI. So the reason that we do training the way we do using these massive compute resources, it's not because AI is complicated, it's because it's complex. It's easy to understand how it works, it's easy to do it, but there's lots of it. And so just the sheer scale of the amount of weights and activation functions and gain parameters that there are means that we can't do it as humans, but computers can do it for us. And so really what I'm saying is that deep learning allows us to solve complex problems using lots of data and computational resource rather than our own ingenuity. Now, I think you can't talk about AI without first of all showing the first diagram that you saw. Then normally the second thing you have to see is the picture of a dog. It could be a cat. I have a slight preference to dogs. So I'm going to use this picture to walk us through the different types of things that a model might be doing with a picture. It's not directly relevant, of course, to embedded AI. This isn't everybody's classical problem, but it does help us see why we have multiple models. So the first thing we might want to do is object detection. So this is just detecting that there is an object in the picture. There's some really, really famous models for doing this. Probably the most famous is YOLO. So YOLO, a lot of people will say, it's that you've got the teen expression, you only live once. Does anybody know what YOLO for the object detection model means? Anybody want to shout it out? Okay, so it's you only look once. And so really what it means by that is that the old way that AI models used to do object detection was they would take the picture and they'd break it into like 8 by 8 or 16 by 16 or 32 by 32 squares. And they'd move through the picture over and over and over again to detect the object. And YOLO revolutionized this by allowing us to detect all of them at once. So the next part is classification. So not only have we detected there's something there, but we know what it is. Now, often, and one of the reasons this is hard to grasp as humans is that we run multiple models all the time. And so for us, when we first saw that picture, we already knew that there was an object in it, and we already knew the object was a dog. And those of us that are interested in dog breeds probably even knew what the breed of the dog was. And if you're really interested in dog breeds, you might have even known what this particular weird coloring is called in the dog breed world. But AI models don't. And so having an AI model that detects objects is different than an AI model that classifies objects, particularly if you know you only want to do one sort of classification. So say the only thing that you're writing in an app, and the only thing that app needs to do is classify dogs. There's no point using a really large model that can classify dogs, cats, humans, teacups. You don't need that part. And so by having multiple models, one that does the object detection, collects that object, feeds that object into the next model, which does the classification, that then allows us to move to the next step. So apologies if this doesn't come out very clear. It says dog, color, white, brown, size, medium. So now we've taken, say, something like YOLO that recognizes that it's a dog and fed it into another model, which now says what tells us more about that dog, brings out the color, and it makes an estimate of its size. Okay, now we're getting much, this is actually quite a difficult problem to solve if you try to do it by hand. One of the great things about AI is it's nearly always unnecessary now to train models from scratch. Again, covered much more in my previous talk, but transfer learning is how we do AI today. Basically, what that means is taking the success of everybody else and then just tuning it a little bit for your need. So you can imagine this is quite a complex classification. So having a model that can say that this dog is an American Cocker Spaniel, and it can also say what type of parakeet a bird is, or what type of cat a cat is, or what type of car a car is. If it could do all of that, imagine the number of parameters you would need. And so if you know that all you need to do is classify a dog breed, you can choose a smaller model. If you knew you needed to classify 5 different things, you could have 5 small models. The object detector and classifier would then choose the small model that would then do the next stage of classification for you. If we're looking at things like security, that would be something that detects motion and then detects if it's human, and then perhaps does face recognition to see if it's you and it's your house, that the door just opens for you, or maybe even it does pose estimation so that it detects it's you, and then it looks at your pose to decide what to do next. If you wave, the door opens. If you do this, the door locks. Each of those could be a separate model, and I'll talk about why in a moment. Recognition. So it's interesting whether this is actually harder than the classification. So feeding a model saying that this dog's called Megan and then it recognizing that it's Megan is actually a very different problem than it just recognizing that any dog is an American Cocker Spaniel. And now we have descriptive. So this is much more closer to using a small generative AI model. This is a Cocker Spaniel dog in a forest. The dog is standing up and looking to the left of the picture. So you can imagine the level of complexity as we go through this changes. And so it's important that we use models of the complexity we need so that we are within size and power budgets for what we're trying to do at the edge. Just out of interest, and I think the picture actually from this distance maybe doesn't allow you to do it, but what I was planning to say was I think that as humans looking at this, we could probably even detect some form of emotion. We could probably look at the dog and say, that dog has seen something interesting. Its ears are just lifted up ever so slightly. It seems to be like staring intensely. And that's something which AI models aren't ready to do at the edge yet, but it's something which I think a lot of you, especially if the picture was a better quality, you would get just by looking at this picture. And so some of the hardest things about designing AI is realizing that no matter how amazing it appears to be, it can only do what it's trained to do. And as humans, we have spent our life in a constant training loop. And so we can do things in many more modals and in many more in many more applications than you can in an AI model. Okay, so we now have 3. And so this is, again, just to kind of show you how the models work. Object detection would detect that there's 3 objects. Then each of these objects, one by one, would be fed into the classifier. And if the classifier said it was a dog, then the model would be fed into a dog breed classifier. If the model said it was a cat, it might be fed into a cat breed classifier. Um, let's now move a little bit closer to something that we're actually likely to encounter in our embedded engineering. If we think of a typical home assistant, something like an Alexa or a Google Home, the little Wi-Fi symbols are used to indicate when we start talking to the cloud. So for the simplest Echo, the majority of them that are available today, the only thing that's done in the device is the recognition of the word Alexa. So the Echo has a small AI engine in it that can do voice recognition of the word Alexa and 3 or 4 other words that you can teach it or that you can ask it to use. In case you don't like saying Alexa. After that, everything you say is transmitted to the cloud. The cloud then does voice to text. It then takes that text and feeds it into an algorithm to understand what the text means. And from understanding what the text means, it then comes up with an action that should be done. And that information is then sent back to the device, and the device carries out the action. The more recent versions of the Echo change that a little. They have enough AI intelligence inside to convert to do the voice to text. Now, I'm sure you can imagine the amount of data you're no longer sending if all you're sending is text rather than sending voice. Okay, I mean it's massive. So because you're sending substantially less data, you also massively improve your latency. I'm sure most of you have interacted with these voice assistants and they seem slow. And a lot of that's to do with the connectivity. So this reduces the amount being sent and also reduces the latency. Now, when we get to the understand text part, I didn't draw this in because I didn't want to overcomplicate it, but basically when it starts to understand the text, if it can't, it goes back and it says, can you send me the audio? And then it does a comparison. It then looks at the audio to answer your question, but it also looks at the audio and compares that to the text to generate feedback and training so that the next iteration of this module in the Echo device is going to be better. You can turn that feature off. You can put privacy features on any of these devices so that they don't analyze your voice. But if you come from somewhere like I do and you don't let the devices analyze your voice, the chances of you ever being able to go up in an elevator to floor 11 are pretty much zero. And the next level is this. Now, one of the things that I want to be really clear about is that, is that understanding this text isn't the same as a large language model. This is for understanding text for commands like turn on the lights. Okay, so not where we're going to have to research the answer. And so basically, this is also an example of multiple models, because once we get to this stage, we do the voice to text. It looks at the text and it says, do I recognize that? Is that something simple that I can do on my device? And if the answer is no, then we jump back up to the next level. The text is sent to the cloud. If the cloud doesn't understand the text, then the audio data is also sent. So there's like a backup mode, okay? So this is a relatively simple because you're just asking it to do something. Now we're asking it a question, and there's more stages to this. And again, by these being separate models, it means that even though this is running in a data center, running smaller models in a data center costs Amazon or Google less money than running big models. And so they always try and work out what model they need to service your question or to service your request so that they are saving megawatts of processing. So I won't go through this one in detail because I'm sure you can follow it, similar to the previous. However, we're still very much at this stage. And one of the things I really wanted to highlight was that at the moment, Google and Amazon on their home devices aren't using large language models. So what do I mean by that? If I say, computer, when is the next train to London? It'll give me an answer. But when I actually asked it this, which I did when I was writing the presentation, I got some very interesting answers. One of the answers, and I asked exactly the same question. So each time it gave me a slightly different answer. And that's actually, if you think back to your days of doing analog to digital conversion, that's basically adding dither. Okay. And so by adding dither into AI to get different answers is easier than trying to work out why it gives you the wrong answer. So if you ask a question and you don't like the answer, if you ask the question again and it gives you the same answer, you're just going to get frustrated. But that's how machines work, but it's not how humans work, right? If I ask you something and you didn't understand what I asked, I would expect you to say something different the second time. And so by adding dither, which is basically just changing what you've asked slightly, you get a different answer. So I asked this question, when's the next train to London? The first answer I got was, well, you can leave your house, get the number 17 bus to the station, and then get that, and then from there you can get a train. I did it, and so it gave me really detailed instructions and included walking. But it didn't tell me when the next train to London was. It told me when the next train to London was if I went there by bus. And getting to my train station by bus is a nightmare. It's there's not very many buses, and the overlap between the bus timetable and the train timetable is not good. And what I wanted to know was when the next train to London was, because I was just going to drive to the train station. So I asked that question again, got a slightly different answer, but I never actually got the answer I wanted, which is when was the next train. Now, if this was a large language model, I could say, thanks very much, Alexa. What I actually want to know is when the next train is that's departing the station now. So not from my home, but when is the next train from Bracknell Station? I could, change the question. It would already have the context of my previous question, and it would give me a much more intelligent answer. So you may think when you're chatting to your Alexa or to your Google Home, you're using large language models, but we're not yet. We will be soon. And most of the companies that are planning to bring out large language models in their home assistants are probably going to charge a subscription. So you can either have a slightly awkward conversation with your Alexa, or you have a much more personal conversation, but it'll cost you a little bit more. Because it's going to cost Google and Amazon a lot more money to run those models, which is why you have this multiple model approach. Now, taking it away from the cloud, we can put the same principle at the edge. So imagine we have some form of security system, and we start with a couple of sensors. Some dumb sensors that just sense, and also some smart sensors. Not trying particularly to recommend particular devices. I just wanted to highlight, because when I normally do this, people ask me, well, what sort of products can do this? So a little bit like the BBC, I'll say there are other suppliers that also do this, but as an example, the ST Microelectronics ISPU enabled sensors. So what this allows is that nearly everything you see on the screen is turned off. The dumb sensor is turned on, so maybe something like a vibration sensor or a time of flight sensor. The smart sensor, which is the one that has the ML core inside it, is turned on, and that might be like an IMU. So this is maybe something that detects motion, detects breaking glass, some relatively simple AI model. And what we're doing was we're running a really simple AI model here. And when that AI model wakes the device up, it then goes into the IO stage, which is also always on, so that you can always communicate. There are a few other things running here too, which I've hidden, things like global timers and various other bits and pieces. But in general, most of it's turned off. We would then move to the high efficiency, in this case, a Cortex-M. Other microcontroller providers are available, like RISC-V. So a Cortex-M and a high efficiency MPU. High efficiency is just another way of saying low power. So you have high efficiency and high performance, because nobody likes to say low performance. So we have a high efficiency Cortex-M and a high efficiency neural processing unit. This will do is the thing that annoyed me important? Is it a human? Should I be alarmed? And if the answer is yes, it's a human and I should be alarmed, we then wake up the high performance engine. Now, the high performance engine can actually have a totally different sensor suite connected to it as well, because the high efficiency can only process relatively low resolution images. High efficiency can process very large scale images. It can also connect to a display, and it can also connect to the cloud. And so as you progress through these steps, the models become more complex. and require more power to run. Now, the reason this is important is if what you've detected here isn't of interest, your device stays turned off. If it might be of interest, your device turns on. And if it's definitely of interest, we analyze it and we send information to the cloud. By applying this type of technique, if you think of like an application we were involved in a couple of years ago was putting poaching cameras in safari parks. To spot poachers and to alert the rangers to come in and stop anything going wrong. Problem is, that didn't use this. It used a device with a model. The first time they didn't actually use models at all. They transmitted everything to the cloud. Even though they put huge battery packs in, the rangers were going to the cameras that often that the poachers could see the clear trail of where the cameras were and just avoided them. So the whole system was pointless. They then moved to trying to run it at the edge, taking the model from the cloud, optimizing it, making it smaller, running it at the edge. That was a great step forward, but it was still using a lot of battery power. And the reason it's still using a lot of battery power is because every time it saw something, it did everything. Using this solution, at the moment, the cameras have been out in the field for 2.5 years now, and the battery power is still good. Our estimate is that these devices will stay out in the field for 15 years. And that's through the power of not using power, okay? Taking your model, splitting it into smaller chunks, and running them on appropriate sized processors for what the model needs to do. It's easier to design this with one model. If you design it with multiple different models and then only wake it up as you go, your battery life vastly improves. Now, often when I talk about power, people are like, yeah, that's really interesting, but I don't design battery operated devices. I don't work with watches or smart rings. My thing's going to be plugged into the mains. It doesn't matter. I would caution you that if you can reduce the power budget of your device, then you're going to have a smaller PMIC, a smaller inductor, smaller heatsink, maybe no heatsink, maybe no fan. I'm interested in processors. So for me, the processor is the most exciting part of any product. However, the people who are selling your product, your business is interested in the cost of your product. And believe it or not, the processor, the little gem of brilliance in the center is not often the most expensive bit. And so if you can reduce the number of fans, if you can reduce the size of the inductors, if you can reduce the thickness of the cables, the BOM cost of your whole product comes down. So I would urge you, even if power isn't something that you think is important, it is. And even if it doesn't change your product, just imagine how much change it'll have, from a sustainability point of view if everything's low power. So even if you're a software engineer, even if you're an AI modelist, if you make your things more efficient, it saves power, and saving that power will help save our planet. Okay. I did say I would just very briefly mention multimodal because it's different, but people confuse the terms. So often I find in the AI world, we use terms that are specific and therefore helpful because we're being precise. However, they also can be a little bit confusing. So you'll hear people talk about things like anamorphic compute because that sounds much more interesting than saying event-based compute. And it's the same with multimodal. Multimodal just means there's more than one type of input or output. So if something only takes in text, it's unimodal. If it takes in text and video, it's multimodal. Now, it's easy to think in the cloud of things like audio, video, and text. But in the real world that we work in, often multimodal means combining temperature, pressure, vibration, LiDAR, radar, time of flight. And there's different ways we can do this. So there's different ways we can do this. Once we've taken the input, we then have to choose at what point these different modalities are integrated. And I've come up with a really cool way of saying, which is just early, middle, and late. So early just means that you put all the sense data together and feed it into your neural network, and your neural network learns based on all the data. Intermediate means that you have an early stage model that understands the individual modalities, and the output of those models then come together for a further larger model. And then late fusion is basically you do most of your AI processing on the individual modalities and only join them together at the output layer. Thank you very much. Thank you. So that was what I set out to say to you, and I think I'm in time. Yeah. I just wanted to share a couple of other things because I often get asked these. So most of the questions that I get asked afterwards normally involve these. So I'm just going to steal a little bit of time. Feel free to walk away because the talk is now officially over. Um, so people often ask me, so that's great. I want to do that. What should I go buy? Where should I start? What dev kit should I get? And so I just wanted to share kind of like the breadth of different suppliers and devices that are available. And what's great with you being here today at Hardware Pioneers is that most of these brands are probably somewhere on the floor, so you can go and talk to them and say that George Arrow told you to come and talk to them about the whatever device you're interested in. This is almost came off the slide, so I'm going to say it out really loud because it's important. What I've drawn here is illustrative and it's not to scale. Okay, it's just to give you a general idea of levels of performance. The other thing I want to say is that performance here is measured in operations per second. It's not the best way to measure AI performance, but I haven't yet found a better one that's easy to do and share. So it's one of those problems that everybody talks about TOPS because it's the only thing that's easy to talk about, but we all know it's not the best measure. The best measure is actually to generate your model and then try it on lots of different platforms. Sally, if you don't mind me calling you out in the audience, Sally works for a company called Edge Impulse. They're a partner of ours. One of the things they do is they allow you to take your models and spread it across a wide range of different devices and see how it works. I'm available at J1. Right beside us, we've got Sally and Edge Impulse available at J6. So feel free to come and talk to us about AI. But really, here we've got Silicon Labs. They're here today with their XG24, fantastic little microcontroller with an AI accelerant, all the way up, to the NVIDIA Jetson. The high-end AGX, we're looking at like 250 TOPS. Where can you run a large language model? So large language models become available at this level. So NXP have just recently acquired Canara, which is a small Canadian startup that does AI accelerators. So you can combine your favorite NXP microcontroller or microprocessor with a Canara. That'll give you 40 or 50 TOPS. It's enough to run a large language model. Aleph, which were the company that I showed in my demo slide about how to split a model for power. I'm showing one of their low-end devices. They're high-end devices which are available next year, but you can talk to us already if you want to get in on the trial. They use ARM's Ethos U85. That can run a large language model. And then Altera, Qualcomm, SEMA, and NVIDIA are all capable as well. If what I said today was super confusing, you can either say that's because I'm a really bad speaker, or maybe just that you need a little bit more detail. In which case, at Ara, we can help you with any stage of your AI journey, right from the data acquisition through to training your model, choosing the best device deployed on. One of the things I find our customers do is they'll often start with the NVIDIA Jetson dev kit, design their model, do a proof of concept, show that it works, and says, right, how do I now bring that to the real world? And what you do is you look at the Jetson and say, am I using all its power? Do I need this fantastic little baby? And if the answer is no, we can help you choose a smaller device. And what's great is that NVIDIA fully supports us in this mission. So NVIDIA have fully opened up their tool chain to allow people to take their models and train them to run on other people's devices because they know that they're here. And they don't want you to use them to solve a problem that you can solve down here. Okay? And so what they've done is they've recognized that and they've opened up their tool chain to partners like us who can help you take their models and run them at the edge. Thank you so much. If you missed my contact details at the start, there they are again. There's a whole series of AI webinars available at aro.com. And again, I'm here for 2 days. So if you'd like to come and talk, I'm available at J1. But we have a few minutes before the next speaker comes on the stage. So do we have any questions? If not, I'm very happy to take them. We don't have a few minutes. I'm being waved off. Thank you all so much, everyone. And I look forward to speaking to you again tomorrow.